In this video and the coming few videos, we are going to solve some examples on the different amplifier families of the bipolar junction transistor. The first example that we see is an amplifier connected like this. We have the transistor here, we have some resistors, capacitors. This is the V input connected here, this is the V output taken from here. Usually the first question that you will be asked about any amplifier circuit is which amplifier family is this? To which amplifier family this amplifier belongs to? Okay, so in order to answer this question, we have to look at the input and the output. We look at the input is going to which terminal of the transistor, the output is taken from which terminal of the transistor, and then the third terminal will be the common terminal. So here, if we look at the input, for example, we'll find that the input is connected towards the base of the transistor, right? And the output is taken from the collector of the transistor. So the third terminal is the emitter. The emitter is the common terminal. We call that third terminal, we call it the common terminal. This is the terminal that will be connected towards the ground. So here, this amplifier is considered to be a common emitter amplifier. So this is usually the first question, is to identify which amplifier family this amplifier belongs to. So this is a common emitter because the input goes to the base, the output is taken from the collector, so the third terminal, which is the emitter, will be the common terminal. Usually the basic steps in order to solve any amplifier circuit is first you have to solve the DC analysis. And in the DC, you have to start with the DC. I'm going to do it here for the first example only, just to show you the steps, but later we will not solve the DC because we already solved DC examples before, so we are not going to go over the DC stage and then the AC. But here I'm going to show you the different steps only for the first example, just to understand that these are the regular steps that you should do for any amplifier circuit. The first step is you solve DC. And in DC, you have to go back to your circuit here and say that for the DC, all the capacitors will be open circuit. So this branch will disappear. This branch will disappear, and this capacitor will disappear. And the remaining circuit will be, so all capacitors will be open. So the remaining circuit will be something like this. And of course, the DC supplies, they are given to be 12 volts here. So the DC supplies are 12 volt. And then the circuit will look like this. R1, R2, R3, and this is RE, R6. And we have all the values for all the R's, and we have the DC supply to be 12 volt. And then you need to solve this DC circuit. This is a pure DC circuit. You solve it in the same way that we solve DC analysis of the bipolar junction transistor. You need to calculate from this circuit, you need to solve and calculate all the DC currents and VCE, IE, IBs. And once you do that, you will be able to calculate the AC parameters. So the second step after you solve the DC is calculate the AC parameters of the AC of the small signal model. The small signal parameters of the small signal model. Which are what? If you are going to use the pi model, then you need to calculate R pi, you need to calculate the GM, right? You need to calculate RO if there is an early effect. And here, let's see if any early effect was given. So we have here, yes, in the problem already they gave you RO with a certain value, okay? So early effect exists here, but in general, if I give you like VA, the early voltage, you need to calculate RO. If I don't give you the early voltage, then you understand that you are neglecting the resistance RO. This is if you are going to use the pi model in order to solve the AC. If you are going to use the T model, then instead of R pi, you need to calculate RE. And in order to calculate these parameters, you will need these DC currents and the currents, and in addition to the early voltage and the threshold voltage VT, which is 25 millivolt. Once you calculate these parameters, you can go and you replace your transistor with the model. Okay, you replace your transistor with the model, whether the pi model or the T model. You can choose any of them. Both of them should give you exactly the same solution. But in some cases, as we said before, in some cases the pi model will be easier to deal with, and in some other cases the T model will be easier. Usually in the common emitter amplifier, usually using the pi model is easier, because in the pi model the emitter is connected towards the ground, and here the transistor, the emitter of the transistor also is connected towards the ground, so there is a kind of matching between the pi model and the common emitter amplifier. So let's do that. But before we do that, after we calculate the parameters for the AC, let's simplify this circuit a little bit. So we'll go back to our original circuit. We'll simplify it a little bit. So we'll notice something, that when we third step solve the AC for the AC analysis, or what we call small signal, sometimes we call it the AC analysis or the small signal analysis, we are going to deactivate all the DC supplies, right? So all DC supplies will be deactivated. If there's a DC voltage source, then you deactivate it by short circuited, make it zero. Making the voltage source zero means implicitly that you are going to connect it to the ground. So when you deactivate the DC supply here, means that you are going to make the DC voltage source to be zero. If there's a current source, you make it zero. But a current source, in order to make the current zero, you have to replace it with an open circuit. In order to make a voltage source zero, you replace it with a short circuit. So here, you can imagine that this is connected by a battery 12 volt towards the ground. If you want to deactivate this supply, you make it zero. Make it zero means that you short circuit, you replace it with a short circuit, which means that this point will be connected to ground. So our circuit now will look like this. First, we have an AC source. This is the input connected to our input. And then we also said that all the capacitors will be considered in the AC analysis. All the capacitors will be considered to be short circuit in the AC analysis. So the capacitor for the DC appears as an open circuit. Like in this case, what we did in this case, the capacitor was open circuit. In the AC analysis, all capacitors will be short circuit. If it happens that you get an inductor in the circuit, then the inductor in the DC, if you have an inductor, if it happens for some circuits that you have an inductor, okay, a coil, then the inductor for the DC will be short circuit. While for the AC, the inductor will be open circuit. So the inductor for the AC is an open circuit, the capacitor will be short circuit. So all the capacitors in the AC analysis will be short circuit. In addition to that, this resistance is connected to ground, resistance R1, and then this resistance will be also connected to ground, because we said when we deactivate this DC source, then implicitly you are going to connect this to ground, right? So R2 is connected between this point and the ground. So you can plot it like this. R2 between this point and the ground. So you can plot it down, okay? And then the transistor comes. So I'm going, as you see, step by step, and this is what you should do, step by step. The transistor, we have the emitter, we have the collector. The collector will have this resistance R3 connected between the collector and the ground. Why the ground? Because we deactivated the source. So we have R3 between the collector and the ground. And then we have a short circuit. This will be a short circuit. And then R7 between this point and the ground. So the collector will be connected by R3 to the ground, and then the capacitor is short circuit, and then R7 to the ground, and this R7 is the one that we measure our V output from. Then the emitter, we look at the emitter will go to a resistance called RE, and then this capacitor in the AC analysis will be short circuit. So this resistance will be short circuited, right? It will disappear because there is a short circuit across it. A short circuit parallel with it, which means that this resistance will disappear. And we will have only this resistance between the emitter and the ground. This resistance RE between the emitter and the ground. I prefer to work with symbols, and at the last step you can substitute with numbers. And here I prefer always to get an expression for the gain, expression for whatever is requested from you. The expression is more important than the number. That's why I'm working here with symbols, okay, R's. And then at the end you can substitute with numbers. In this part, the expression is much more important than the number, okay? That's why if I ask you to calculate the gain, for example, of this amplifier, and then you just write a number without proof, without getting the expression first, then you will not take any mark for that. You have to show how you got this number, how you derive the expression first, and then at the end, at the last step, you substitute with numbers and you get the final number. So do not substitute with numbers from the beginning, go with the symbols until you get the final expression, then you substitute with the numbers at the end. Now we can simplify this circuit. Why? Because R1 and R2, they are parallel, right? So we can combine them together with a resistance. We will call it RB, for example. So we can combine R1 and R2 with a resistance called RB. And this RB will be R1 parallel with R2, which can be calculated. You can calculate its number. It's 300 parallel with 160. This will give you I guess it will give you around 104 kilo ohm. Let me see here. Anyways, it will give you some number. I don't care about the numbers now. And also you can combine R3 and R7 in one resistance, right? Because they are parallel together. So you can combine R3 and R7, and you can call them any name. You can call it R load, RL, for example. Okay, where you are taking your output voltage from here. So RL is R3 parallel with R7, and you have the values for R3 and R7. You can calculate 100 parallel with 22. So you can calculate whatever the value of RL. So now we simplified our circuit for the AC analysis, and what we can do now is we replace the transistor with the model. And as we said here, it might be easier to use the pi model. And so the next step, we will replace the pi model. But before we do that, let's look at this specific problem. These are the general steps. Okay, you have to solve DC first, calculate the AC parameters, and then you do your AC analysis where you replace the capacitor to short circuit, and all the DC sources will be deactivated. If it is a voltage source, you make it short circuit towards the ground. If it is a current source, you make it open circuit. And then the last step is you replace your transistor with the model. And if we use the pi model here, the pi model will look like this. Resistance R pi, current source, dependent current source, GM VBE or beta I base, whatever is easier for you. If this is I base, then it will be beta I base, in addition to a resistance RO between the collector and the emitter. This is the collector, this is the base, this point is the emitter. So you replace your transistor with the model, and now we have a circuit. Just the circuit that you used to solve in the circuits course. And from this circuit, you will calculate whatever is required from you. For example, here we are required to calculate what is V output over V base, V output over V base. VB is the voltage of the base here. V output over V input. So this is called the gain between V output and V base. This is V output over V input. This is called the overall gain from the beginning to the end of the amplifier. We are required to calculate R input looking at the base and R output looking at the collector. R input and R output can be, I can ask you to calculate R input and R output from different points in the circuit. For example, I can ask you to calculate R output directly looking at the collector, or R output looking from here, for example. And same for R input, I can ask you to calculate R input looking directly at the base, or I can ask you to calculate R input looking from here. I will put an arrow for you to clarify. I want you to calculate R input and R output from which point. So here it was specified that I want you to calculate R input at the base, looking at the base, and R output looking at the collector directly. And basically R input and R output will be doing Thevenin equivalent resistance, looking at the input terminal and looking at the output terminal. So basically we are going to use Thevenin equivalent resistance. So I advise you, if you need to review how to calculate the Thevenin equivalent resistance, specifically Thevenin equivalent resistance, please go and review it before we proceed with the remaining material.